The nearest star beyond our Sun is 4.25 light years away. Light makes that journey in just over 4 years. Voyager 1, the fastest spacecraft humanity has ever launched, would need roughly 75,000 years. We have left Earth. We have walked on the moon. We have crossed every planet's orbit. We have sent machines beyond the edge of the solar system. And in all that time, we have traveled almost nowhere at all. The emptiness between stars sounds peaceful. It is anything but. Interstellar space is filled with high energy radiation capable of breaking apart human DNA, microscopic grains of dust that would strike a fast moving spacecraft with the energy of explosive projectiles, and distances so immense that no emergency message could ever return home within a human lifetime. For decades, physicists, biologists, and aerospace engineers have been asking the same unsettling question, not whether we can build a spacecraft fast enough, but whether the people inside it could survive what comes next. Every obstacle appears to have a solution. Build a faster engine, carry more shielding, create artificial gravity, put the crew to sleep. Then another problem emerges beneath it. What happens when a spacecraft moves through the interstellar medium at one-fifth the speed of light? What does a lifetime of isolation do to the human mind? How does time itself separate a crew from everyone they have ever known? And if they somehow survive the journey, what kind of people step out at the other end? The greatest challenge of reaching another star may have almost nothing to do with rockets. It may be biology, it may be psychology, it may be the simple fact that human beings evolved to live on one small planet beneath one ordinary star. If this kind of content helps you unwind at night, consider subscribing. We put out new space documentaries regularly, and having you here means a lot. It starts with the closest destination beyond our solar system and a distance that completely changes the meaning of the word far. Imagine placing your finger on a map where no road exists, then realizing the destination is already known. We are not searching for an unknown shore anymore. We already have an address. Its name is Proxima Centauri, the closest star beyond our Sun, resting about 4.25 light years away. That equals roughly 40 trillion kilometers, which is about 24.9 trillion miles. The distance sounds enormous until we remember what a light year truly means. It is simply the distance that light covers during one full year while racing through space at about 300,000 kilometers every second, which is about 186,000 miles every second, fast enough to circle Earth roughly 7 times before a single second has ended. Around that faint red star circles a world called Proxima Centauri b. Astronomers confirmed its existence during the year 2016 through careful measurements of its parent star's motion. The planet travels inside what scientists call the habitable zone. That is the region around a star where temperatures could allow liquid water to remain on a planetary surface. It appears to possess at least a little more mass than Earth, making it one of the nearest places where familiar conditions might exist. We cannot promise oceans, clouds, or even an atmosphere. We only know that it deserves our attention. But distance shapes every part of the story. If you hope to reach Proxima Centauri within about 20 years, your spacecraft would need to cruise near one-fifth of the speed of light. Our fastest machines today move at only a tiny fraction of that pace, about 6 thousandths of 1% of light speed. The difference between those values is not a minor engineering upgrade. It is an entirely different chapter in the history of technology. For this journey, we will accept one generous assumption. Somehow, somewhere, humanity solves propulsion. We build a vessel capable of crossing the gulf between stars within a human lifetime. The engines work, The fuel problem yields. The ship keeps accelerating until the destination finally becomes reachable. That leaves the question that matters: what happens to the people inside? Everything from this point forward rests upon that single decision. We will not spend our time wondering whether the engines ignite. We will ask what unfolds after they do. As the familiar influence of the sun fades behind the ship, another environment slowly takes its place. The change is almost impossible to notice with human senses, yet instruments would record it without hesitation. From that moment onward, the greatest challenge may no longer be the spacecraft itself. It may begin inside every person aboard, shaped by something few travelers would ever expect to fear. There is no line painted across space to announce that you have left home. No wall appears ahead of the ship. No change unfolds outside your window. Yet there comes a measurable instant when every instrument aboard agrees that the familiar influence of our star has finally reached its limit. Astronomers call this boundary the heliopause. It marks the place where the outward flow of charged particles streaming from the sun can no longer overpower the pressure of the wider galaxy. Our solar system has never ended with a planet. It ends with a fading shield. Humanity first crossed that threshold during August of the year 2012. Voyager 1 reached the heliopause after traveling roughly 18 billion kilometers, which is about 11.2 billion miles, from the Sun. Light itself needs approximately 18 hours to bridge that distance. The spacecraft carried no passengers. Even so, it became the first object built by human hands to enter the space between the stars. But the crossing was far from empty. Voyager 1 immediately detected a sharp increase in galactic cosmic rays. These are extremely energetic atomic particles arriving from distant events across the Milky Way. Their numbers rose as soon as the protective influence of the sun weakened. At nearly the same moment, the familiar magnetic environment that had surrounded the spacecraft for decades gave way to a different one, shaped by interstellar space itself. The transition was unmistakable. We rarely notice how well protected we are. Earth possesses its own magnetic field, wrapping our planet in a broad magnetic cocoon that deflects many dangerous charged particles before they ever reach the atmosphere. Around that lies the heliosphere, the vast bubble carved by the solar wind throughout the surrounding galaxy. Together, these two natural barriers reduce most of the energetic radiation that would otherwise sweep across Earth's surface every day. A crewed vessel leaving the solar system surrenders both forms of protection. First, the planet disappears behind it. Later, the heliopause falls away as well. From then onward, every person aboard enters an environment no human body has occupied for more than brief journeys beyond Earth's immediate surroundings. Even the Apollo expeditions passed through the Van Allen radiation belts, regions where charged particles become trapped by Earth's magnetic field in only a matter of hours. Imagine watching a display aboard the spacecraft as the readings steadily climb. Nothing visible surrounds the ship. Nothing strikes the hull with a flash, yet the numbers continue changing, recording a place where nature follows different rules than those protecting the world where you were born. The boundary exists in physics before it exists in human experience. We cross it once, and the voyage becomes something fundamentally different. What fills that immense darkness is almost impossible to see, yet it carries consequences that reach into every living cell aboard the ship. Unlike the hazards we usually imagine, this one has no color, no sound, and no obvious direction. It fills the space between stars with relentless persistence. We call these travelers galactic cosmic rays. They are atomic nuclei, mostly hydrogen nuclei, alongside heavier nuclei such as iron, carbon, and silicon, hurled across the galaxy by exploding stars and other violent cosmic events. Some have wandered through interstellar space for millions of years before meeting anything at all. They do not arrive as a single stream. They come from every direction at once, above you, below you, ahead and behind. Every side of a spacecraft faces the same invisible bombardment. Turning the ship changes almost nothing. The particles simply find another path. When one passes through the human body, the damage differs profoundly from an ordinary medical scan. Heavy atomic nuclei moving at extraordinary speeds carve an intensely concentrated trail of ionization, meaning they strip electrons from atoms as they pass through living tissue. That narrow path tears through cells, sometimes breaking both strands of the deoxyribonucleic acid double helix at the same time. This represents one of the most difficult forms of genetic injury for cellular repair systems to correct, increasing the chance that permanent mistakes remain after healing. Evidence has already reached human eyes. During the Apollo expeditions beyond low Earth orbit, several astronauts described sudden flashes of light while their eyes were closed. They were fully awake. Researchers later confirmed that energetic particles had passed directly through the retina and optic nerve, producing genuine visual sensations without any external source of light. The brain briefly interpreted radiation itself as sight. But those missions lasted only days. Crews aboard the International Space Station, spending roughly 6 months in orbit, typically receive between about 72 and 80 millisieverts of radiation. That already exceeds the annual occupational guideline of 50 millisieverts applied to many radiation workers on Earth. Extend the voyage across roughly 20 years toward another star, and estimates rise to approximately 1,400 millisieverts before accounting for additional radiation released during powerful stellar eruptions from Proxima Centauri. The numbers carry human consequences. At that accumulated exposure, lifetime cancer risk increases by roughly 5 to 7 additional percentage points above the ordinary baseline. Picture a crew of 10 people beginning the journey together. Statistics suggest one additional person may eventually develop cancer that otherwise might never have appeared. Yet, cancer tells only part of the story. Researchers studying prolonged radiation exposure have uncovered another effect that reaches beyond damaged genes and altered cells. It touches the organ responsible for judgment, memory, planning, and personality itself. The radiation challenge can, in principle, be reduced through sufficiently effective shielding. Engineers understand that much. Once they began calculating the amount of protection required, however, the mathematics revealed another obstacle waiting beneath the first. Picture the walls around the crew becoming thicker with every new calculation. Each added layer promises greater protection. Each added layer also changes everything else about the journey. Physics rarely offers gifts without asking for something in return. Researchers have explored several materials capable of reducing the effects of galactic cosmic rays. Dense substances absorb more incoming radiation, giving the crew a better chance of avoiding long-term biological damage. Lead has attracted attention for generations because it blocks many forms of radiation with remarkable efficiency over relatively short distances. Water has become another serious candidate because every voyage already requires large reserves for drinking, food preparation, and life support. Polyethylene, a durable plastic rich in hydrogen, also performs well against many energetic particles. Even liquid hydrogen itself has been studied as a possible protective barrier. But every option carries a cost. Lead shields extremely well, yet it is extraordinarily heavy. Calculations show that surrounding a crew compartment with enough lead to provide meaningful protection could require more mass than the spacecraft itself. A vessel designed to carry explorers would gradually become a vessel designed mainly to carry shielding. Water offers a more elegant compromise. Tanks can be positioned around living quarters, so the same supply, sustaining life, also reduces radiation exposure. Engineers appreciate this efficiency because every kilogram serves more than one purpose. Even then, the amount required remains immense. The walls protecting the crew would still contain an enormous volume of material that must accompany the ship for the entire voyage. The story becomes even more complicated when energetic particles strike those protective layers. A galactic cosmic ray colliding with dense material can produce secondary radiation, creating fresh particles that continue traveling inward. These include neutrons and gamma rays, both capable of harming living tissue. Add too much lead, and some calculations predict the crew may receive increased exposure from the new radiation created inside the shielding itself. More protection can unexpectedly generate another hazard. Everything returns to mass. Every additional kilogram placed aboard must eventually be accelerated to roughly one-fifth of the speed of light. The energy needed to achieve that speed rises along with the spacecraft's total mass. Stronger shielding demands more propulsion. Greater propulsion usually demands more fuel. More fuel increases mass again. The cycle repeats without offering an obvious escape. Scientists have also imagined protecting the ship with magnetic fields instead of thick walls. Earth already demonstrates the principle. Our planet's magnetic field deflects many charged particles before they reach the atmosphere. Reproducing such a protective bubble around a spacecraft for decades, however, would require powerful systems operating continuously across the entire mission. The engineering remains unresolved, and so do the enormous energy demands. Suppose, for a moment, that these obstacles become manageable. The crew receives enough protection to keep radiation within acceptable limits. Another challenge still waits, entirely unrelated to cosmic rays. It begins the instant gravity releases its hold on the human body, and every passing day strengthens its influence. Long before we learned to build spacecraft, gravity had already shaped every cell within us. Across roughly 500 million years of vertebrate evolution, life adapted to a world that always pulled downward. Bones, muscles, blood vessels, and even the balance centers of the brain developed with that steady pull as a constant companion. Remove it, and the body does not simply float, it begins rewriting itself. Bone is often imagined as solid and permanent. In reality, it is living tissue under constant renovation. Specialized cells continually remove old bone, while others replace it with new material. On Earth, walking, standing, and lifting provide the mechanical signals that encourage fresh bone to form. During prolonged weightlessness, those signals fade. Cells responsible for breaking down bone continue their work while bone building slows. The result is a gradual loss of roughly 1 to 2% of bone density each month in weight-bearing regions such as the hips, the thigh bones, and the lower spine, but the arithmetic becomes startling over decades. Without an effective countermeasure, a traveler spending about 20 years in deep space could lose between roughly 20 and 40% of skeletal density. Bones that once absorbed tremendous force begin resembling those weakened by advanced osteoporosis. A stumble during landing, a sudden maneuver, or even an unusually powerful muscle contraction could produce fractures in places that once seemed unbreakable. Muscles follow a similar path. The deepest muscles of the back, the legs, and the core exist largely to resist gravity every waking moment. Once gravity disappears, many of those tissues lose their primary purpose. Wasting begins within days. Astronauts, spending approximately 6 months aboard the International Space Station, commonly return with about 20 to 30% less muscle mass in the lower body, despite carefully planned exercise throughout their missions. The heart changes as well. It is, after all, another muscle. In weightlessness, body fluids drift toward the head instead of pooling in the legs. The heart no longer works as hard to lift blood upward against gravity, so it gradually becomes smaller and less powerful. When normal gravity suddenly returns beneath your feet, that reduced heart must immediately meet demands it has not faced for years. Blood pressure can fall sharply. Standing itself may become difficult. Vision also shifts. Increased fluid pressure inside the skull has been associated with flattening of the rear portion of the eye and swelling around the optic nerve. This condition, known as spaceflight associated neuroocular syndrome, has affected roughly 40% of astronauts on long duration missions. For some, eyesight never completely returns to its earlier state. Imagine arriving after decades of travel, carrying brittle bones, weakened muscles, a diminished heart, and damaged vision. Every essential task on an unfamiliar world would demand a body performing at its absolute best. Yet biology has been moving in the opposite direction since departure. Preserving that biology throughout the journey appears possible only if gravity itself somehow accompanies the crew, bringing us to one of the most ambitious engineering ideas ever seriously proposed for human spaceflight. Instead of changing the human body, imagine changing the world around it. That single idea has guided engineers for generations. If gravity cannot travel with us naturally, perhaps it can be created through motion itself. The only method confirmed by known physics is rotation. Spin a habitat continuously, and the outward force pressing against its inner walls begins to resemble the familiar pull you have experienced since birth. The principle is surprisingly straightforward. A rotating structure pushes everything inside toward its outer edge. That pressure imitates gravity, allowing people to stand, walk, and work much as they would on Earth. Yet the mathematics refuses to be flexible. A small habitat must spin rapidly to create Earth normal gravity. A much larger habitat can rotate more gently while producing the same effect. Comfort, therefore, depends heavily upon size. But rotation introduces another complication. Whenever you move through a spinning environment, your path bends in unexpected ways because of what scientists call the Coriolis effect. This apparent force causes objects and people to drift sideways relative to their intended direction. Many individuals experience dizziness, nausea, and confusion until the brain gradually adapts. Research suggests that adaptation becomes much easier inside very large rotating habitats. Current studies indicate a radius of roughly 250 meters, which is about 820 feet, offers a practical lower limit for avoiding severe discomfort during everyday movement. Now consider what such a structure truly represents. A habitat extending 250 meters from its center, which is about 820 feet, must support living quarters, life support systems, food production, water recycling, storage, maintenance equipment, and enough redundancy to survive decades without outside assistance. Every kilogram must then be accelerated to roughly 1/5 of the speed of light. The numbers become so immense that realistic cost estimates remain largely unexplored. Some engineers have proposed a compromise. During the long cruise between stars, part of the spacecraft could unfold and rotate, then retract again before major propulsion events. The concept reduces some of the difficulties while introducing many others. Bearings, joints, connection points, and mechanical locks would need to perform flawlessly across approximately 20 years without opportunities for replacement. Current astronauts rely on another strategy. Aboard the International Space Station, they spend roughly 2 hours exercising every day to reduce the loss of bone and muscle. The routine helps considerably. It does not eliminate the problem, even over missions lasting only about 6 months. Extend that same approach across 20 years, and the remaining physical decline becomes deeply uncertain. We arrive at an uncomfortable balance. Without artificial gravity, the crew reaches another star weakened. With exercise alone, they remain healthier, yet still diminished. A vast rotating habitat offers the most convincing path toward preserving human biology, while demanding an engineering effort almost beyond present imagination. There is, however, another possibility. Rather than protecting the body throughout every passing day, perhaps the body could spend most of the voyage unaware that those days are passing at all. Perhaps the most remarkable solution asks us to do almost nothing at all. Instead of protecting an awake crew through every passing day, we place them into an artificial state of profound metabolic dormancy and allow the voyage to unfold while their bodies consume only a fraction of their usual energy. On paper, the idea seems almost perfect. Food requirements shrink, life support becomes simpler, isolation nearly disappears. The long years pass without being consciously experienced. Nature already offers several examples. Ground squirrels spend months in deep hibernation. Bears slow their metabolism dramatically through winter. The fat-tailed dwarf lemur, the only known primate capable of true hibernation, can remain dormant for extended periods while reducing body temperature, slowing the heartbeat to only a few beats each minute, and conserving energy with extraordinary efficiency. When these animals awaken, they have preserved far more muscle and bone than ordinary inactivity would suggest. The secret lies within their biology. During hibernation, specialized pathways controlling protein production help protect muscle tissue from wasting away. Changes involving the hormone osteocalcin contribute to preserving bone. Even the immune system reorganizes into a protective state suited for prolonged dormancy. Human beings possess no natural version of this remarkable adaptation. Our bodies simply never evolved for it. But medicine has taken cautious steps in a similar direction. Researchers, supported by the National Aeronautics and Space Administration, have explored forms of induced hypothermia for future spaceflight. Hospitals already lower body temperature during certain cardiac procedures and after severe injuries to reduce metabolic demand. These treatments usually last hours. Occasionally, they extend somewhat longer. Beyond roughly 1 or 2 days, however, the biological consequences become increasingly uncertain. Stretching that process across decades remains entirely beyond demonstrated medical experience. Then comes the greatest uncertainty of all. No animal has ever been awakened after spending years in continuous dormancy, much less decades. Bringing a human being back without organ failure, neurological injury, or collapse of the immune system remains an unanswered scientific question. Extending lessons from bears directly to interstellar travelers moves beyond established evidence into carefully reasoned speculation. Another difficulty refuses to disappear. Radiation continues regardless of whether the crew is awake. Galactic cosmic rays still pass through the spacecraft. They still damage deoxyribonucleic acid within living cells. In fact, dormant tissue may prove even less capable of repairing that damage because many cellular repair processes slow alongside metabolism itself. Imagine opening your eyes after what feels like a single night's sleep, only to discover that 20 years have vanished. Earth is now more than 4 light years behind you. End quote. Conversations with home unfold across nearly a decade. Every meaningful decision must begin immediately. Remarkably little research has explored the psychological consequences of awakening into such circumstances. For now, suspended animation remains an active field of investigation rather than an available technology. The first crews attempting interstellar travel will almost certainly remain awake throughout the journey, carrying every passing year with them as they drift between the stars, where another challenge has already begun reshaping the human mind itself. Long before anyone spends decades between the stars, we have already rehearsed fragments of the experience here on Earth. Crews have lived beneath the ocean inside submarines. Researchers have endured entire winters at Antarctic stations. Volunteers have entered sealed habitats built to imitate journeys toward Mars. Different places, different missions, yet remarkably similar patterns emerge whenever human beings remain confined together for long enough. Psychologists have given one of those patterns a memorable name. They call it the third quarter phenomenon. During missions with a known ending, emotional strain rarely reaches its highest point at departure or arrival. Instead, tension rises after the excitement has faded, while the destination still feels frustratingly distant. Familiar routines become repetitive, minor disagreements gather weight, patience slowly becomes harder to sustain. But an interstellar voyage offers no natural landmarks for the nervous system. Seasons never arrive. The sky outside never announces spring or autumn. Sunrise and sunset become artificial schedules rather than planetary events. Every week resembles the last, making the passage of time strangely difficult to feel, despite calendars continuing their steady count. Observations from Antarctic winter expeditions reveal how this environment shapes the mind. Irritability often increases within roughly 3 months. Persistent sleep disruption commonly develops by about 6 months. Researchers have also documented cognitive blunting, meaning a measurable reduction in the complexity of thought, language, and mental flexibility. Relationships within small groups often grow unusually intense. Lifelong friendships may form. Lasting resentment may also take root. There is remarkably little middle ground. Those studies lasted months. Our imagined voyage lasts 20 years. Privacy presents another challenge that receives surprisingly little attention. Throughout human history, people have almost always possessed some opportunity to step away from others. A forest path, an empty shoreline, or a separate room could provide temporary distance. A spacecraft offers no such guarantee. Every compartment exists beside another. Every movement occurs within a shared environment. Over many years, the inability to become genuinely alone may develop into a constant psychological pressure. Leadership also changes with time. The commander who departed Earth may become elderly, seriously ill, or no longer capable of serving. Authority may shift gradually or fracture unexpectedly. Earth cannot settle those disputes. Any message requesting guidance requires more than 4 years to arrive, while the reply needs another journey of equal length. Decisions must already be finished long before advice appears. Perhaps the most significant finding from long-duration isolation research concerns neither memory nor physical coordination. It concerns judgment itself. The ability to interpret unfamiliar situations accurately and choose wisely appears especially vulnerable after prolonged confinement. That is precisely the ability every crew depends upon when unexpected events unfold, far from every place humanity has ever called home. Complex systems operating across decades eventually encounter failure, and the setting surrounding this voyage gives those failures consequences unlike any experienced before. Engineers have a phrase that sounds almost harmless until you watch it unfold. They call it a failure cascade. The idea is straightforward. In any sufficiently complex system, one small malfunction rarely remains isolated. Every component depends upon another, and each dependency creates another path through which trouble can spread. By the time the final consequence appears, the original fault may seem almost insignificant. We have already witnessed how modern spacecraft survive through constant support. The International Space Station receives fresh supplies roughly every 90 days. Food arrives, spare parts arrive, medicines arrive, new instruments replace aging ones, crews rotate home while others take their place. Every delivery interrupts problems before they have years to accumulate. But an interstellar vessel receives nothing at all. Everything the crew will ever touch departs with them. Every replacement valve, every circuit board, every medical instrument, every filter, and every spare bearing already occupies its place before launch. If an unexpected failure demands a component that was never packed, the mission must continue without it. Reliability, therefore, becomes a mathematical exercise, unlike almost any attempted before. Suppose a critical system must remain dependable across 20 years. Achieving reliability, approaching 99.9%, demands several completely independent backups, yet every backup is another intricate machine with its own chance of failure. Those backups require additional power, maintenance, structural support, and replacement parts. Mass steadily grows, and every extra kilogram must still accelerate toward 1/5 of the speed of light. The ship also carries another population. Since November of 2000, the International Space Station has remained continuously inhabited. Microbiological surveys have revealed that bacteria and fungi adapt surprisingly quickly under prolonged exposure to microgravity and radiation. Some strains have developed resistance to antibiotics beyond that observed in closely related populations on Earth. Others have shown mild corrosive effects on metal surfaces. Inside a sealed vessel operating for 20 years, those microscopic communities continue evolving, whether anyone notices or not. Medical uncertainty compounds the challenge. A crew member could develop appendicitis. Another might suffer kidney stones. Brittle bones weakened through years away from gravity increase the danger of severe fractures. Radiation may contribute to cancers that emerge long after departure. If the voyage spans generations, childbirth introduces another layer of complexity. Every treatment depends entirely upon the knowledge, equipment, and medicines already aboard, while Earth remains 4.25 light years away. Now imagine a single chain of events. A tiny micrometeoroid opens a narrow breach. Repair systems compensate, placing additional demand upon life support. Carbon dioxide slowly rises inside the habitat. Elevated carbon dioxide subtly reduces concentration and decision making. One mistaken judgment alters a navigation procedure. Correcting that mistake consumes more fuel than planned. Reduced reserves remove options during arrival. None of those failures alone ends the mission. Together, they reshape its outcome. But that is the defining feature of a cascade. Every individual problem appears manageable until the accumulated consequences reach a point where nothing earlier in the chain can be reversed. Even then, Every challenge still belongs to familiar categories of engineering, biology, or psychology. As the ship approaches its extraordinary cruising speed, the universe introduces an entirely different kind of hazard, one governed by physics itself, rather than by the machine carrying us. Imagine placing your hand into falling snow. Individual flakes barely register. Now imagine moving through that same snowfall at a speed approaching one-fifth of the speed of light. The snow has not changed. You have. That difference reshapes everything we understand about empty space. Interstellar space contains remarkably little matter. Most of it is hydrogen and helium, spread so thinly that the average density is only about one atom within each cubic centimeter. Mixed among those atoms drift microscopic grains of silicate, carbon, and iron, ancient debris forged during stellar explosions and the birth of planetary systems. At ordinary speeds, these particles scarcely matter. A spacecraft could cross enormous distances without noticing almost any of them. But velocity transforms insignificance into danger. The energy carried by a moving object rises with the square of its speed. Increase velocity enough, and even a tiny particle becomes devastating. A dust grain, weighing 1 milligram, smaller than an ordinary grain of sand, approaching at one-half of the speed of light, carries about the same kinetic energy as a 100-kilogram person traveling at 13 kilometers per second, which is about 8 miles per second. Such a particle does not ricochet away from the hull. It releases its energy almost instantly, producing a localized explosion capable of blasting through solid material. This concern is far from theoretical. During 2016, researchers examining the breakthrough starshot concept estimated that a probe weighing only a few grams and traveling toward Alpha Centauri at one-fifth of the speed of light would experience roughly 100,000 dust impacts. During its journey, a probe can survive through careful shaping of its forward surface, but a crewed spacecraft would expose a vastly larger area to those same collisions, multiplying the challenge accordingly. Dust is only part of the story. Hydrogen atoms, the most common particles between the stars, become relentless projectiles at these extraordinary speeds. They strike the leading surface with energies comparable to beams produced inside powerful particle accelerators. Each impact penetrates materials, disrupts delicate electronics through ionization, meaning electrically charged damage inside matter, and steadily transfers heat into the ship's forward structure. The consequence is difficult to ignore. Calculations indicate that the leading edge of a spacecraft traveling at one-fifth of the speed of light could remain as hot as the surface of a vehicle plunging through Earth's atmosphere during re-entry. But re-entry lasts minutes. This heating would continue throughout a voyage lasting 20 years. No material currently known can preserve full structural integrity under those conditions for such an extraordinary span. Researchers have even suggested that physics itself imposes an upper practical limit. A study published during 2012 argued that hydrogen bombardment alone makes travel beyond roughly one-half of the speed of light increasingly destructive for both electronics and living occupants. The faster we attempt to cross the gulf, the more the gulf pushes back. But that realization carries another consequence. If survival demands a slower journey than ambition prefers, then distance regains its power, and time becomes the next obstacle we cannot simply outrun. Time itself now becomes part of the journey. We often imagine it as a steady current flowing equally for everyone, everywhere. Modern physics paints a different picture. According to Albert Einstein's special theory of relativity, confirmed repeatedly through experiments of extraordinary precision and even corrected for daily in the operation of global positioning system satellites, a moving clock truly runs more slowly than one at rest. This is not a measurement error. It is woven into the structure of space and time. At one-fifth of the speed of light, the effect remains modest, yet it is measurable. During a voyage lasting 20 years aboard the spacecraft, the crew would age about 2% less than people who remained on Earth. By the time the mission reached its destination, the travelers would be roughly 5 months younger than their Earth-bound contemporaries. Interesting, certainly. Transformative, not yet. But increase the speed, and the difference grows. At four-fifths of the speed of light, 20 years experienced aboard the ship correspond to roughly 33 years passing on Earth. The travelers celebrate the same birthdays they expected, while calendars at home advance much farther. Push the journey to 9/10ths of the speed of light, and the separation widens again. 20 years aboard become about 46 years for everyone left behind. The famous twin paradox begins to feel deeply personal. Imagine an astronaut departing Earth at 30 years of age. After 20 years aboard a spacecraft traveling at 9/10ths of the speed of light, that explorer reaches the destination still only 50 years old. Former classmates are now 76. Children waving farewell on launch day have entered their middle 50s. Elderly parents, if they were fortunate enough to witness departure, have almost certainly vanished into history. For a one-way expedition, this is no paradox at all. It becomes permanent separation. The crew does not merely cross an immense physical distance, they also cross into a different moment of human history. They arrive carrying memories from a civilization that has continued changing without them. In a profound sense, they become visitors from their own past. Communication deepens the divide, even across the comparatively short gulf separating Earth from Proxima Centauri. Every message requires years to travel. A question transmitted at departure may receive its reply roughly 8.5 years after it was first asked, and that answer already describes an Earth that no longer exists by the time it arrives. Conversation stretches into generations instead of moments. But the isolation extends beyond distance, psychology, or delayed communication. It reaches into time itself. The crew arrives detached from the era that launched them, unable to step back into the world they once knew. Ahead waits a neighboring star, familiar in astronomical catalogs, yet astonishingly different in practice, carrying one overlooked reality that reshapes nearly every expectation we bring to the destination. Long before the crew can examine their destination directly, the character of its parent star has already shaped the mission's greatest uncertainty. Proxima Centauri belongs to a family known as red dwarfs, stars far smaller, cooler, and dimmer than our Sunday. They are remarkably common, making up roughly 70% of all stars in the Milky Way galaxy. In most respects, Proxima Centauri is an ordinary member of that vast population. Only its closeness to Earth makes it extraordinary to us. Its size hides a volatile nature. Red dwarfs concentrate powerful magnetic fields within compact interiors. Those tangled magnetic fields repeatedly snap and reconnect, releasing enormous bursts of electromagnetic radiation and streams of charged particles. These eruptions are called stellar flares, sudden explosions that greatly exceed the activity our own sun usually produces. One event revealed just how violent this neighboring star can become. During March of 2016, astronomers observed a flare that caused Proxima Centauri to brighten by a factor of 68 in ultraviolet light within only a few seconds. Estimates suggested that this single eruption released roughly 10 times more energy than the strongest solar flare ever recorded from our Sunday. For observers on Earth, it appeared only as changing light collected by telescopes. For any nearby planet, the experience would have been profoundly different. Proxima Centauri b circles its star at a distance about 20 times closer than Earth orbits the Sunday. Because the star shines much less brightly, that orbit still falls within the habitable zone, the region where liquid water could exist on a planetary surface under suitable conditions. But proximity comes with an unavoidable cost. Radiation intensity rises dramatically as distance decreases. Even moderate stellar flares become far more dangerous when experienced from so close. Calculations indicate that during a major flare, ultraviolet radiation reaching the surface of Proxima Centauri b could approach 100 times the level considered hazardous for human exposure on Earth. Unprotected human tissue would receive a lethal radiation dose within minutes. Any future explorers would require substantial shielding or carefully timed shelter whenever the star erupted. But the atmosphere itself may face an even greater challenge. Repeated storms of charged particles gradually erode planetary atmospheres across immense spans of time. Whether Proxima Centauri b still possesses a substantial atmosphere depends largely upon the existence of a global magnetic field capable of deflecting that continuous bombardment. At present, no observation has confirmed whether such a magnetic shield exists. The planet almost certainly keeps the same face turned toward its star. This condition, called tidal locking, means one hemisphere experiences endless daylight while the opposite hemisphere remains beneath perpetual darkness. Between them lies a narrow region of lasting twilight, where temperatures may prove less extreme. Winds on such a world could circulate continuously between blazing warmth and intense cold, creating weather unlike anything humanity has experienced. But every conclusion we have reached remains an inference drawn from distant measurements of starlight and subtle gravitational motion across 4.25 light years. The destination awaiting the crew may prove welcoming, hostile, or something entirely unforeseen. They cannot know which until they finally arrive. We have devoted years of thought to a world that remains almost entirely hidden from direct view. Every prediction rests upon a handful of measurements gathered across an immense gulf of space. The planet called Proxima Centauri b is one of the most discussed destinations beyond our solar system, yet almost everything about it remains uncertain. Its discovery was elegant. During 2016, astronomers confirmed the planet through the radial velocity method, a technique that measures tiny shifts in a star's light as an orbiting planet gently pulls it back and forth. This motion creates a subtle change in wavelength through the Doppler effect, the same phenomenon that changes the pitch of a passing siren. From that motion, we can calculate a minimum planetary mass. Beyond that, the method reveals remarkably little. The unanswered questions quickly multiply. We do not know whether Proxima Centauri b possesses an atmosphere. If one exists, we do not know its composition or its pressure. We cannot say whether oceans cover its surface, whether continents rise above them, or whether widespread volcanism continually reshapes the landscape. Its magnetic field remains undetected. Its axial tilt is unknown. Even the presence of natural satellites remains an open question. But one possibility has captured extraordinary attention. If future observatories detect an atmosphere rich in oxygen, the finding would become one of the strongest hints of biological activity beyond Earth. Oxygen reacts readily with surrounding materials and normally disappears unless some ongoing process continually replaces it. On Earth, living organisms perform that task. Current telescopes cannot determine whether Proxima Centauri b possesses such an atmosphere, although the next generation of space observatories may eventually gain that capability. The opposite outcome carries equal weight. Should the crew arrive and discover no atmosphere at all, decades of preparation would culminate on an airless world exposed directly to intense radiation. Every expectation of settlement would vanish immediately. The destination would become a place for observation rather than a place for lasting habitation. But an atmosphere alone offers no guarantee. A sky dominated by carbon dioxide, methane, ammonia, or sulfur dioxide would remain deeply hostile to human biology. Surface operations would require sealed habitats from the first landing. Those shelters would need to be assembled by explorers already shaped by a journey lasting 20 years, on terrain whose geology and environmental hazards had never been examined firsthand. The greatest uncertainty reaches beyond survival. Suppose unmistakable evidence of living organisms greets the expedition. The mission would instantly transform from exploration into first contact with an independent biosphere. Every decision would carry ethical consequences. Would our arrival preserve that world, alter it, or unintentionally damage forms of life that evolved entirely apart from Earth? Mission planners therefore confront a remarkable paradox. Every plausible outcome demands specialized equipment, procedures, and reserves, yet every additional kilogram increases the burden carried across 4.25 light years. The ship must prepare for possibilities that cannot be narrowed before departure. But every unknown waiting ahead shares one remarkable feature. None can be resolved until arrival, while another transformation has already begun within the travelers themselves, unfolding gradually beneath the steady influence of interstellar radiation. Long before the crew reaches another star, something less visible has already begun changing within them. The alteration leaves no scar, triggers no alarm, and offers no unmistakable warning. Yet, it affects the organ upon which every decision, every calculation, and every hope of success ultimately depends: the human brain. Among the many hazards of deep space, this remains one of the least discussed outside scientific circles. Galactic cosmic rays do more than raise the lifetime probability of cancer. Evidence gathered during the past decade suggests they can reshape the structure and function of the brain itself. Researchers supported by the National Aeronautics and Space Administration at the University of California, Irvine exposed laboratory mice to simulated galactic cosmic ray environments designed to resemble the radiation expected during prolonged missions beyond the protection of Earth's magnetic field. Their findings appeared in peer-reviewed scientific journals and have since been reinforced through additional investigations by independent research groups. What they observed reached deep into the nervous system. Dendrites, the branching extensions that allow nerve cells to receive signals from neighboring neurons, became shorter and less complex within the prefrontal cortex. This region supports planning, judgment, attention, and the careful weighing of consequences. As those delicate branches retracted, the network itself grew less connected. The architecture of thought had begun to change. Behavior changed as well. Animals exposed to the radiation displayed greater anxiety, diminished curiosity, weaker performance during complex navigation tasks, and reduced flexibility when confronted with unfamiliar problems. Sustained attention also declined. These are precisely the abilities an interstellar crew would depend upon when confronting equipment failures or unexpected discoveries many light years from home. But the most unsettling feature lies elsewhere. The decline appears gradually. There is no single day when someone suddenly realizes their judgment has become unreliable. Instead, each small change blends into the next. A crew member may feel entirely capable while making decisions that are measurably less accurate than those made years before. Confidence survives. Performance slowly erodes. The numbers deepen that concern. Current career exposure guidelines established by the National Aeronautics and Space Administration limit astronauts to approximately 600 millisieverts of radiation. Estimates for a minimally shielded 20-year interstellar voyage approach 1,400 millisieverts. The neurological changes observed in animal studies emerged at exposures well below that cumulative total. But radiation would never act alone. Sleep disruption, prolonged isolation, monotony, and persistent psychological stress all influence the same cognitive systems. Each burden compounds the others. No laboratory has ever recreated all these conditions together across 2 decades, because no environment matching such a mission has ever existed. We therefore arrive at a remarkable possibility. The explorers entrusted with deciding whether to descend, whether to remain in orbit, whether the destination is safe, or whether the mission must end, may be making those choices with minds that have been gradually reshaped by the journey itself. Momentum has carried the crew across the gulf between stars. Now that same momentum becomes the final obstacle. A spacecraft that has spent 20 years building extraordinary speed cannot simply arrive and stop. Every kilometer traveled has stored motion that must somehow be surrendered before the destination disappears behind it forever. The numbers are staggering. After 20 years of travel, the vessel approaches the Proxima Centauri system at roughly 60,000 kilometers per second, which is about 37,300 miles per second, close to one-fifth the speed of light. At that velocity, the entire distance from Pluto's orbit to the Sun would be crossed in approximately 12 minutes. Unless the ship slows successfully, it will rush through the planetary system and continue into interstellar space beyond it. But slowing down demands almost as much as speeding up. The energy required for deceleration closely matches the energy invested during acceleration. Any propulsion system that consumes stored fuel must therefore preserve enough reserves for the return to lower speed. Those reserves travel aboard the spacecraft throughout the voyage, adding mass from the first day, while remaining unavailable for every unexpected challenge encountered along the way. The burden grows heavier. Consider a vessel driven by nuclear pulse propulsion, a concept often viewed as more plausible for transporting people than the highest speed proposals. Even if such a ship reached only about 3% of the speed of light, the journey would extend across many decades. Yet the mathematics remain unchanged. The fuel intended for stopping cannot be borrowed for emergencies, corrections, or unforeseen demands without placing the entire arrival at risk. But engineers have explored other possibilities. One proposal imagines deploying an immense magnetic sail, a magnetic field extending outward to interact with the stellar wind flowing from Proxima Centauri. The idea resembles using the star itself as a brake. Calculations suggest this approach may help very lightweight robotic probes. For a crewed spacecraft weighing millions of kilograms, however, the available braking force appears far too small. Another possibility borrows a technique used closer to home. Aerobraking slows spacecraft by allowing atmospheric drag to absorb energy during repeated passes. The method has proven valuable around Mars, yet it depends completely upon knowing the atmosphere in advance. If Proxima Centauri b possesses an atmosphere that is thinner than expected, the ship escapes back into space. If the atmosphere proves denser, friction may destroy the vehicle before orbit is achieved. Everything, therefore, depends upon timing. The deceleration burn must begin at precisely the calculated moment. Begin too soon, and the spacecraft exhausts its fuel before completing the maneuver. Wait too long, and no remaining thrust can prevent the ship from racing beyond the system. Earth cannot correct that decision. Every message requires years to cross the distance separating the two civilizations. But imagine the calculation succeeds. The engines fall still, the spacecraft settles into orbit, and the travelers finally reach the world that has filled their thoughts for 2 decades. Their greatest challenge is no longer the journey through space, but stepping into a reality that 20 years of preparation could never fully rehearse. Some journeys ask us to solve engineering problems. Others ask us to confront questions that engineering cannot answer. A voyage lasting centuries belongs to the second kind, because the greatest uncertainty is no longer machinery or propulsion. It is the people who will inherit the mission long after its founders are gone. A multi-generational expedition cannot be sustained by a handful of travelers. Studies in population genetics suggest that preserving healthy genetic diversity across many generations requires roughly 500 to 1,000 individuals. Instead of a crew, the spacecraft becomes a settlement. It carries schools, families, traditions, disagreements, celebrations, and eventually people whose ancestors remember Earth only through stories. But only the first generation chooses to leave. Every child born aboard the vessel enters a life already decided by someone else. You and we can imagine accepting the voyage for ourselves. Those children never receive that invitation. Their destination, purpose, and future exist before their first breath, and no nearby horizon offers another path. Beyond the hull waits only interstellar space. No existing legal system fully addresses such a reality. International maritime law, space law, and constitutional traditions all assume continuing ties with Earth. Rights, governments, and institutions ultimately exist within societies that remain connected to a homeworld. A generation ship slowly loses that connection until every decision must arise from within the community itself, without courts, elections, or outside authorities capable of meaningful intervention. But history suggests that cultures never remain unchanged. The values established at launch may endure for decades before gradually evolving into something unfamiliar. Language shifts, customs acquire new meanings, rituals replace forgotten memories. By the time the descendants approach their destination, the civilization that designed the mission could feel as distant as ancient Rome feels to people living today. Instructions written centuries earlier may still guide daily life, even though those following them no longer share the assumptions of their creators. Institutions also change. Organizations rarely preserve their original purpose indefinitely, even with continual renewal. Inside an isolated spacecraft, every governing structure must correct its own mistakes without external oversight. If authority slowly drifts toward dysfunction, no neighboring nation exists to intervene, and no larger civilization provides an alternative example. The arrival generation, therefore, inherits more than a spacecraft. They inherit expectations formed before they existed. Their childhood unfolds beneath manufactured skies, illuminated by artificial light. Rain belongs to archived recordings. Soil survives inside carefully managed gardens. Unfiltered sunlight exists only in lessons passed from teacher to student across centuries. When they finally stand beneath the sky of another world, every familiar instinct about distance, weather, gravity, and open landscapes must be learned almost from the beginning. But success can no longer be measured only by reaching another star. It must also be measured by the lives shaped across generations that never cast a vote for the journey, a possibility that may prove more attainable than a 20-year crossing, and one that leaves us facing an even deeper question about whether humanity should go simply because it eventually can. Seen from a greater distance, the voyage itself begins to fade, leaving only the machines we have actually built. Before imagining the next century, it helps to pause beside the hardware that already exists, because the contrast between aspiration and reality is where the scale of this challenge becomes unmistakable. The Parker Solar Probe currently holds the record as the fastest human-made object ever launched. During its closest passes above the Sun, it reaches roughly 692,000 kilometers per hour. That is about 0.064% of the speed of light. Its protective shield withstands temperatures approaching 1,370 degrees Celsius, or about 2,498 degrees Fahrenheit. Even with that astonishing performance, a journey to Proxima Centauri would still require roughly 6,500 years. But speed alone does not tell the whole story. Voyager 1 has been traveling outward since 1977 at about 17 kilometers per second, which is about 10.6 miles per second. That equals only about 0.006% of the speed of light. It remains the most distant human-made object ever constructed. Around 40,000 years from now, it will pass within roughly 1.6 light-years of a star known as Alpha Camelopardalis, plus 79 3888. It will not enter orbit there. It will simply continue drifting, carrying a record of its creators, long after every nation, institution, and language that launched it has changed beyond recognition. New Horizons offers another perspective. It achieved the fastest departure from Earth ever accomplished by a spacecraft, reaching roughly 58,000 kilometers per hour. That carried it to Pluto in only 9 years. At that pace, however, Proxima Centauri remains nearly 78,000 years away. Distances between stars transform remarkable achievements into patient beginnings. But the numbers become even more revealing when placed side by side. A practical 20-year crewed mission demands travel at roughly 20% of the speed of light. The Parker Solar Probe reaches only 0.064%. Closing that gap requires an increase of approximately 300 times. This is not the sort of improvement gained through stronger engines or lighter materials. It represents an entirely different era of propulsion, one that has not yet arrived. The most credible proposal, now under active discussion, reflects that reality. Breakthrough Starshot envisions an extremely small probe weighing about 1 gram, pushed by an immense ground-based laser array until it reaches roughly 20% of the speed of light. The required infrastructure could cost tens of billions of dollars. Yet the probe cannot slow down, cannot carry people, and can gather information only during a brief passage lasting mere seconds before vanishing into the darkness beyond the Proxima Centauri system. Taken together, these machines provide the clearest measure of our progress. They are extraordinary achievements, yet they also reveal how immense the remaining distance truly is, encouraging us to look beyond propulsion alone and toward an even deeper question about why humanity feels compelled to cross the gulf between the stars. A conversation over lunch can sometimes outlive entire scientific careers. In 1950, physicist Enrico Fermi looked beyond equations and asked a remarkably direct question. If intelligent civilizations are common within a galaxy containing roughly 200 billion to 400 billion stars, many of them billions of years older than our sun, where is everybody? The question still echoes today. Even conservative calculations produce an unsettling result. A civilization capable of building self-replicating probes, machines able to construct copies of themselves using local materials, could spread from star to star without requiring enormous populations. Traveling far below the speed of light, such probes might still cross the Milky Way over only a few million years. Against the age of the galaxy, that interval is astonishingly brief. Yet when we look outward, we find no confirmed evidence that anyone has already done so. But one explanation is simple. Perhaps technological civilizations are extraordinarily uncommon. This idea, often called the rare Earth hypothesis, suggests that the chain of events leading from chemistry to intelligent observers may be so improbable that planets like ours almost never produce them. We may not be completely alone, yet we could belong to an exceedingly small community scattered across unimaginable distances. Another possibility feels more unsettling. Civilizations might emerge repeatedly, only to fall quiet before spreading between the stars. Some researchers describe this obstacle as the Great Filter, a stage difficult enough that very few societies ever survive beyond it. If that barrier still lies ahead of humanity, then every achievement we celebrate today could represent only the beginning of a far greater test. But there is a third interpretation grounded in physics itself. Perhaps no civilization has discovered a practical way to overcome the immense separation between stars. Every challenge we have explored, radiation, weakening bodies, changing brains, accumulating failures, enormous energy demands, and relentless impacts from interstellar dust, arises from physical laws that appear universal. Any beings living beneath another sun would confront those same laws. Their technology might differ from ours, yet the universe would impose identical limits. From that perspective, the apparent emptiness above us acquires a different meaning. The sky may not be empty because nobody ever existed. It may appear empty because every civilization reaches the same boundary and spends its history looking across an ocean too vast to cross. Distance itself becomes the great divider, preserving countless islands of intelligence that never truly meet. But there remains another way to understand the silence. Instead of asking what the absence of visitors reveals about distant civilizations, we can ask what our persistent desire to leave our own world reveals about humanity. That shift moves the question away from the stars themselves and toward the species standing beneath them, still looking upward, still building, and still wondering whether reaching across the darkness is valuable even if the journey can never become easy. Some ideas reshape the way we look at the entire universe. The Great Filter is one of them. Proposed by economist Robin Hanson in 1998, it suggests that somewhere between simple chemistry and a civilization capable of spreading across the galaxy lies an obstacle so overwhelming that almost no species ever passes beyond it. The apparent emptiness surrounding us hints that such a barrier may truly exist. But its location changes everything. If the Great Filter lies behind us, then the hardest chapters have already been written. Perhaps the truly improbable step was the origin of life itself. Perhaps it was the appearance of the eukaryotic cell a cell containing specialized internal structures that made greater biological complexity possible. It could have been the evolution of sexual reproduction or the emergence of large, reasoning brains. In that view, the universe appears empty because those milestones almost never occur. The alternative carries a different weight. Suppose civilizations commonly reach our present level of technology before encountering a challenge that consistently ends their progress. The silence overhead then becomes less comforting. It resembles a warning carried across immense spans of time. Every society eventually reaches the same invisible threshold, and very few continue beyond it. But interstellar travel stands directly at that threshold. If biological humanity never escapes the solar system, then our future remains tied to a single star. In about 1 billion years, the sun will gradually brighten until Earth's surface becomes too warm for stable liquid oceans. Long before the sun reaches the end of its life, roughly 5 billion years from now, the world supporting us today will already have become hostile to complex life. Closer dangers exist as well. Around 66 million years ago, an object roughly 10 kilometers across, which is about 6.2 miles, struck near what is now the Yucatan Peninsula. About 75% of Earth's species disappeared during the resulting catastrophe. The released energy approached 100 teratons of explosive force. Astronomers have identified most Earth-crossing asteroids larger than 1 kilometer, which is about 0.62 miles, yet the inventory remains incomplete. Our planet also remembers violence from below. Roughly 74,000 years ago, the Toba supervolcano erupted with extraordinary force, and some evidence suggests the global human population may have fallen to only about 10,000 individuals. The Yellowstone volcanic system last erupted around 640,000 years ago. It remains geologically active, reminding us that immense eruptions belong to Earth's natural history. Each threat differs in origin, yet all point toward the same conclusion. A civilization existing in only one place remains vulnerable to a single catastrophe. Spreading across multiple worlds offers the only enduring protection against every danger acting on one planet alone. But the nearest possible destination still waits 4.25 light years away, and everything we have explored together reveals just how immense that crossing truly is. Measured against deep time, every human achievement carries an ending already written into its future. Every empire has faded, every dominant language has changed, every political order has yielded to another. Even the longest continuous cultural tradition we know, maintained by Australian Aboriginal peoples for roughly 65,000 years, represents an extraordinary human legacy that remains almost invisible beside the age of the cosmos. The contrast is immense. In about 5 billion years, the sun will swell into a red giant. Mercury will disappear first. Venus will follow. Earth may also be engulfed, although its exact fate depends upon the changing outer layers of the expanding star. But our oceans will not survive anywhere near that long. As the sun slowly grows brighter, they are expected to vanish within roughly 1 billion to 1.5 billion years, leaving our world unable to support the rich complexity of life we know today. But our own story occupies only a tiny interval. Human civilization emerged during the final fraction of the universe's history so far. Our species has existed for only about 0.002% of the age of the cosmos. Every disagreement, every invention, every work of art, every economic system, and every philosophy belongs to a civilization still living on a single world, circling a single ordinary star. Viewed this way, Interstellar travel becomes less an expression of ambition than arithmetic. If humanity never spreads beyond one planet, our ending remains tied to that planet's future. The exact cause may differ. It could arrive suddenly through catastrophe, or gradually through astronomical change. Either path eventually reaches the same destination. At present, the only conceivable way to extend the human story beyond the lifespan of one habitable world is to establish life around another star. But honesty requires another admission. Even successful journeys between stars cannot defeat every limit imposed by nature. The universe itself continues evolving. Over incomprehensible spans of time, stars exhaust their fuel. Galaxies drift farther apart as the expansion of spacetime increases the distances separating them. Some physical theories even suggest that matter itself may ultimately decay. Nothing we have imagined allows biological life to escape every future transformation awaiting the cosmos. Those timescales scarcely resemble anything life has experienced. Perhaps this is why the challenge feels so deeply personal. We often imagine interstellar travel as a problem of engineering, budgets, or determination, yet the greater obstacle lies elsewhere. We are confronting a universe whose physical laws existed long before biology appeared, and those laws never promised that creatures like us would move easily between the stars. But another fact deserves equal attention. Against staggering odds, the universe produced beings capable of understanding their own impermanence. We can calculate these distant futures. We can recognize our fragile place within them. That awareness was never guaranteed, and somehow it gives the vast silence around us a different kind of meaning. For most of human history, our ancestors lifted their eyes toward the night sky without knowing what those distant lights truly were. The understanding that stars are other suns emerged only within the last few centuries. The first confirmed discovery of a planet orbiting another ordinary star came less than 30 years ago. The confirmation that a planet circles the nearest star to our own is newer still, arriving within the lifetime of many people alive today. That realization changes everything. We are the first generation in the history of our species that can point toward a specific world, 4.25 light years away, and say with confidence that it exists. We know how long its year lasts. We know its minimum mass. We know the star it circles. We also know, with equal precision, the extraordinary cost demanded by the journey between here and there. But knowledge has outpaced ability. Perhaps that is the defining feeling of this moment. We can identify the destination. We can calculate the distance. We can estimate the dangers awaiting along the way. Yet, every honest calculation leaves us standing on the same shore, aware of the opposite coast while lacking a vessel capable of crossing the sea between. Earlier explorers accepted uncertainty of a different kind. The navigators of the great sailing voyages crossed immense oceans, believing that land might exist beyond the horizon, though none could prove it beforehand. Their maps contained blank spaces. Their confidence rested upon possibility. Our situation has almost reversed that relationship. We know Proxima B is there. We simply cannot visit it, and we cannot discover directly whether it resembles the hopes carried within our imagination. But our telescopes continue turning toward it. Each observation becomes an unusual act in human history. We are studying a destination already identified, fully aware that nobody living today is likely to stand upon its surface. Every improvement in our instruments sharpens a portrait that remains forever incomplete, adding another careful brushstroke to a landscape viewed across 4.25 light years. The night sky no longer appears as an endless scattering of anonymous lights. Instead, it resembles a chart marked with real places, measured distances, and carefully recorded unknowns. Among those countless stars, one small red sun now carries a name familiar to millions, along with a nearby planet that has become a destination in thought long before it becomes one in practice. But perhaps that transformation matters as much as any future voyage. The effort to understand worlds beyond our reach reveals something remarkable about the minds asking the questions. We are a species that measures impossible distances, accepts uncomfortable truths, and continues looking outward anyway. In that persistence, long before the first interstellar journey begins, we may already recognize something essential about who we are. Across the immense history of life on Earth, one pattern stands apart from all the others. Paleontologists estimate that roughly 5 billion species have lived and vanished across our planet's long biological story. Countless forms learned to hunt, hide, cooperate, compete, and adapt. Yet only one species ever looked beyond survival, lifted its gaze toward the stars, and wondered what waited there. Only one began building instruments to answer that question, then calculated the staggering price of crossing the darkness itself. That distinction deserves our attention. Language alone does not explain it, neither does tool making or cooperation. Other animals communicate, solve problems, and pass knowledge across generations. What appears genuinely unusual is the combination of abstract curiosity about places impossibly distant and the willingness to pursue those answers across centuries, knowing that many of those who begin the work will never witness its conclusion. But perhaps no object captures that impulse more completely than the Voyager record. In the year 1977, the National Aeronautics and Space Administration placed a golden record aboard each Voyager spacecraft. The record is a copper disc covered with a layer of gold, created to preserve sounds and images from Earth for an unimaginably long journey. It carries greetings spoken in 55 languages. It carries music ranging from Johann Sebastian Bach to Chuck Berry. It preserves the sounds of rain, breaking waves, laughter, footsteps, and the first words spoken by a mother to her newborn child. Today, those records continue outward. They have become the most distant human creations ever sent into space. Long after every generation alive at their launch has disappeared, they will continue traveling between the stars. Tens of thousands of years from now, they will still not have reached another stellar system. Their voyage unfolds on a timescale almost impossible for human lives to comprehend, but they were never expected to be found. The likelihood that another civilization encounters either record is extraordinarily small. Their value was never measured by the probability of success. Instead, the records express something truthful about the civilization that created them. They declare that we recognized our own existence, imagined that others might exist as well, and considered it worthwhile to send a greeting across distances so immense that any reply would arrive far beyond the lifespan of every person who first conceived the idea. The same impulse appears throughout our exploration of the universe. It inspires observatories, equations, spacecraft, and dreams of voyages still beyond our reach. None begins with certainty. Each begins with the belief that understanding something distant is valuable even when the reward cannot be guaranteed. But perhaps that is the most remarkable discovery of all. A universe governed by uncompromising physical laws also produced a species unwilling to let those laws define the limits of its curiosity. Judged only by efficiency, that persistence may appear irrational. Judged across the whole history of life, it may be the most profoundly rational thing we have ever done. Nothing announces the beginning. There is no visible line where the solar system ends and interstellar space truly begins. Instead, you notice change through accumulation. The familiar world behind you grows smaller with each passing day, until Earth becomes impossible to distinguish from the light surrounding its parent star. Within hours, it has already become a pale point. Within days, the sun is simply the brightest star among countless others. But the sky keeps changing. For years, many constellations remain recognizable. Gradually, however, their familiar shapes begin to bend. Nearby stars shift against more distant ones through parallax, the apparent movement created by viewing the galaxy from a steadily changing position. Patterns that guided humanity for thousands of years slowly dissolve into new arrangements that no civilization on Earth has ever named. Eventually, you reach the midpoint. At roughly 2 light-years from both the Sun and Proxima Centauri, neither star deserves to be called home more than the other. Earth has vanished completely, hidden within the Sun's brilliance and invisible without powerful instruments. Every city, every mountain, every ocean, every memory exists in a direction you can indicate with certainty, yet never reach within your remaining lifetime. But the view outside remains astonishing. Without an atmosphere, starlight never flickers. Each point remains perfectly defined against a darkness deeper than any night experienced beneath Earth's sky. The Milky Way stretches overhead with extraordinary texture, revealing lanes of dust and crowded rivers of distant suns. You no longer look outward at the galaxy, you exist within it. Time continues its patient work. The calendar aboard the ship records 20 years. Faces have aged by 20 years. Friendships have matured. Children never arrived. Seasons never changed, and weather never interrupted another ordinary day. For roughly 7,300 days, life unfolded within recycled air, familiar corridors, familiar voices, familiar machinery, and walls that never moved farther apart. No wind crossed your skin. No rain fell from above. No natural horizon separated land from sky. But another horizon finally appears. Proxima Centauri grows from a brilliant point into a discernible disk, glowing with a subdued reddish light that instruments resolve long before human eyes can. Then the planet emerges. At first it resembles another distant star. Slowly it becomes a sphere, carrying unfamiliar colors and patterns, shaped beneath the light of a sun unlike our own. One hemisphere remains bathed in perpetual daylight, while the other never sees dawn. Between them lies the narrow boundary where day and night meet. The crew gathers at a window. No calculation can prepare them for this moment. Every equation, every sacrifice, every engineering compromise, every year spent crossing interstellar space has led here. They stand 4.2, 5 light-years from every human life that has ever unfolded on Earth, looking upon a world no member of their species has ever seen directly. Beyond the glass waits everything they hoped for, everything they feared, and everything they still cannot know. Long before any human being crossed the gulf between stars, another traveler had already turned to look back. In the year 1990, at the request of astronomer Carl Sagan, Voyager 1 rotated its camera toward home from a distance of roughly 6 billion kilometers, which is about 3,728,000,000 miles. Earth appeared as less than a single pixel, a tiny fleck suspended within a ray of scattered sunlight. It was a reminder that perspective can change everything without changing anything at all. From the vicinity of Proxima Centauri, that perspective grows even more striking. our sun becomes one faint star among countless others, carrying no obvious importance from that distant vantage. Earth disappears entirely, hidden within that tiny point of light. Every civilization, every conflict, every discovery, every poem, every friendship, every triumph, and every mistake belongs to a world that cannot be seen without powerful instruments. Distance has compressed the whole human story into something effectively invisible. But you know it is there. The people standing beside that porthole carry its entire inheritance with them. Their bodies preserve an evolutionary history measured across millions of years. Their languages echo generations of teachers and storytellers. Their knowledge reflects countless minds working across centuries, each contributing another small piece to an understanding that finally made this journey possible. For every practical purpose, they are the only living representatives of their home anywhere nearby. They did not arrive alone. Behind them stretches an uninterrupted chain of decisions made by people who would never witness the destination themselves. Engineers accepted problems that resisted solution. Scientists measured realities that seemed almost beyond comprehension. Entire societies invested resources, patience, and belief into an outcome that remained uncertain across lifetimes. But each generation carried the effort a little farther than the one before. The impulse reaches much deeper than modern technology. It belongs to the same instinct that encouraged early humans to walk beyond familiar valleys without knowing what waited ahead. It belongs to navigators who steered wooden vessels across open oceans, guided only by memory, observation, and trust. It belongs to those who placed a golden record aboard Voyager 1, understanding that discovery sometimes matters even when no reply is expected. Measured in practical terms, the cost has always been immense. Trillions of dollars, decades of preparation, generations of research, and 20 years spent living inside an artificial world represent sacrifices that can be counted. The scientific return cannot be counted so easily. Until arrival, every conclusion remains provisional, every expectation vulnerable to surprise. But another result has already emerged. By reaching this place, humanity has answered a question older than civilization itself. We did not learn whether another world would welcome us. We learned something equally enduring. Faced with impossible distance, uncertain reward, and the indifferent laws of physics, we remained the kind of species that crossed the darkness anyway. After everything we have measured, calculated, and imagined together, one question still remains. The title asks whether the first humans to leave our solar system will arrive. The only honest answer, assembled from every challenge we have explored, is that we do not know. The radiation may prove greater than biology can endure. The propulsion may never reach the required speed. Minds may struggle beneath years of confinement before the edge of the solar system is even behind them. Deceleration may fail after decades of flawless travel. The destination may offer no refuge. A generation ship may slowly lose the purpose that launched it. A single unexpected failure may unfold into consequences no engineer could fully predict. But another future remains equally possible. Each obstacle may yield a little at a time. One discovery may improve shielding. Another may reshape propulsion. New materials may emerge from laboratories that have not yet been built. Observatories may reveal details about nearby worlds that today remain hidden from us. Every generation could inherit questions that seem impossible, then solve one of them before passing the rest onward. Progress has often arrived in steps too small to notice until viewed across centuries. The deeper question, then, is not whether the first travelers arrive, it is whether the first travelers choose to leave at all. That decision must be made without certainty, without guarantees, and without the promise that success will belong to those who begin the journey. You and I can recognize that pattern because it has appeared throughout our history. Every horizon once seemed absolute. Sailors crossed oceans whose far shores existed only in rumor. Polar explorers entered landscapes from which many never returned. The first astronauts climbed aboard machines that had never carried human beings beyond Earth. None of those moments came with certainty. Everyone demanded imperfect knowledge, incomplete technology, limited time, and the willingness to continue despite all three. But the horizon before us stretches farther than any before it. The distance is measured in light years rather than oceans. The risks unfold across decades rather than months. The consequences reach beyond individual lives into the future of an entire species. Even so, the structure of the choice has changed less than you might expect. We gather evidence. We calculate carefully. We acknowledge every danger we can identify. Then we decide whether understanding is enough to justify the attempt. Perhaps that is the most enduring discovery of all. Beyond the mathematics, beyond the engineering, and beyond every map we have drawn, we find something that belongs neither to physics nor astronomy. We find a species capable of understanding how immense the universe truly is, while continuing to look toward it anyway. If you remain beneath the night sky long enough, the stars gradually stop feeling like distant lights. They become reminders that curiosity itself may be the longest journey humanity has ever begun. Even now, while you rest beneath the same sky that has accompanied this entire journey, another traveler continues onward. Voyager 1 is moving through interstellar space at about 17.3 kilometers per second, which is about 10.7 miles per second. Its nuclear power source grows weaker with every passing year. Current projections suggest that sometime between the middle and later years of this decade, its remaining scientific instruments will finally fall inactive. After that, the spacecraft itself will continue alone. Nothing waits to stop it. Unless a distant star alters its path through gravity, Voyager 1 will keep traveling for ages beyond ordinary imagination. In roughly 40,000 years, it will pass within 1.6 light years of a star in the constellation Camelopardalis. That approach remains far too distant for capture, yet close enough for gravity to leave the smallest signature upon its course before the journey resumes. Its companion follows another path. In approximately 296,000 years, Voyager 2 will pass about 4.3 light years from Sirius, the brightest star in Earth's night sky. Far beyond those encounters, after roughly 4 billion years, both spacecraft will have completed a single orbit around the Milky Way galaxy. One circuit across a galactic path nearly 100,000 light years wide, around a home containing between 200 billion and 400 billion stars. The voyage continues regardless of whether anyone is watching. But one object aboard Voyager 1 carries a different kind of endurance. The golden record may survive beyond the lifetime of Earth's oceans. It may endure after the sun leaves, the stable stage of its life that has sustained our world for billions of years. It could even outlast the planet that gave it form. No human artifact has ever been entrusted with a longer future. It is already between the stars, accomplishing something no person from our century is expected to experience directly. That is a remarkable fact. In the most literal sense possible, humanity has already sent part of itself into interstellar space. Aluminum, gold, plutonium, wiring, and carefully assembled electronics are crossing the thin material between the stars at this very moment. These probes are not symbols invented for inspiration. They are physical machines still traveling while you listen, carrying evidence that something built on Earth escaped the boundary of our solar system. But they were never meant to solve the hardest part. Machines do not fear isolation. They do not suffer radiation sickness. They do not lose hope after years beneath the same ceiling. They require no destination that feels like home. Every challenge we have explored belongs to the presence of human beings, not to the motion of a spacecraft. That difference between transmitting measurements and living the journey itself is where the true weight of this story rests. Sitting with that distinction beneath a sky filled with destinations still beyond our reach, the distance somehow becomes easier to understand, even while it remains unchanged. Long before anyone understood what a star truly was, they were already overhead. Every human being who has ever lived, across roughly 300,000 years of anatomically modern humanity, inherited the same night sky. Proxima Centauri shone above the earliest people in Africa. It remained there above every traveler, every storyteller, every child who wondered about the scattered lights, and every civilization that rose, flourished, and disappeared without realizing those distant points were other suns. For almost all of that history, the stars belonged to mystery rather than measurement. They guided journeys, inspired beliefs, and marked the changing seasons. Their beauty was unmistakable, yet their physical nature remained hidden. Only within the last century did we learn that stars are immense spheres powered by nuclear fusion, the process in which light atomic nuclei combine and release extraordinary amounts of energy. Only within the last few decades did we confirm that planets circle many of them. Then, only recently, we identified a particular world around the nearest star and could finally say there is a destination 4.25 light years away. That change happened astonishingly fast. 300,000 years of looking became about 100 years of understanding. Understanding became barely a decade of knowing the address, yet the ability to travel there still waits beyond our reach. Knowledge has raced ahead of capability, leaving us in a rare moment when the map exists long before the road. But imagine explaining our present to those who came before us. They would hear that we know another world circles the nearest star. They would learn that we can measure its distance in kilometers, which is about 40 trillion kilometers, that is nearly 25 trillion miles. They would discover that we understand how radiation affects living tissue, how gravity shapes planetary systems, and how the space between stars challenges every spacecraft we can imagine. Such knowledge would seem miraculous. Our inability to make the journey, however, would probably surprise them far less. Every generation has inherited truths that exceeded its tools. The pace of discovery offers another perspective. The first confirmed detection of a planet beyond our solar system came in the early 1990s. The nearest potentially habitable world around Proxima Centauri was confirmed in the middle of the 21st century's second decade. The James Webb Space Telescope, launched in the early years of this decade, has already begun examining the atmospheres of distant planets with a level of detail that scarcely seemed possible only a few years earlier. Progress rarely follows a straight path, yet it continues to accumulate. But the stars never hurried. They have remained where they always were, keeping their own timescale while humanity gradually learned to read the sky. Somewhere beyond the darkness, 4.25 light years away, one small world continues its orbit, waiting exactly as it always has for whatever generation finally becomes ready to make the crossing. Some challenges reshape us long before they yield an answer. They demand decades of patience, generations of cooperation, and the willingness to work toward outcomes we may never personally witness. Interstellar travel belongs to that rare category. Its apparent impossibility is part of what gives it such remarkable power. A problem that already appears solvable rarely changes an entire civilization. One that seems beyond reach often does. History offers familiar examples: heavier than air flight, controlled nuclear energy, sequencing the complete human genome, and detecting gravitational waves, each spent years under serious scientific doubt. Those doubts did not come only from uninformed critics. Many respected researchers examined the available evidence and concluded the barriers were simply too great. But deeper investigation gradually revealed that the obstacle lay within human understanding rather than within nature itself. The laws of physics remained exactly the same. Our picture of those laws became clearer. That pattern deserves attention. Every generation inherits an incomplete map of reality. As observations improve and theories mature, boundaries that once seemed fixed sometimes move farther away. There is no guarantee that interstellar travel will follow this path, but there is equally no evidence that discovery has reached its final chapter. The universe has surprised us before, often when confidence appeared strongest. Today, the obstacles remain substantial. Propulsion systems still fall far short of the required performance. Radiation shielding demands, materials, and engineering beyond our present capabilities. Long duration life support, meaning ecosystems capable of sustaining people for decades without outside assistance, continues to challenge researchers. Suspended animation, the idea of safely slowing biological activity for extended periods, remains an active field rather than an established technology. Yet none of these disciplines has reached a confirmed theoretical limit. Each continues to advance, one careful experiment at a time. But progress also depends on intention. The Breakthrough Starshot initiative represents an important turning point, regardless of its eventual outcome. For the first time, a serious, well-funded scientific effort has focused specifically on engineering a path toward another star. Whether its concepts succeed matters less than the fact that humanity has begun treating interstellar travel as an engineering question instead of only a philosophical one. Every ambitious field begins somewhere. The effort produces rewards long before departure. Materials science becomes stronger. Propulsion physics grows more sophisticated. Radiation biology deepens our understanding of living tissue beyond Earth. Closed ecological systems, meaning environments that recycle air, water, and nutrients without continual resupply, become more practical. Artificial intelligence, designed for autonomous decisions across many years, improves alongside them. Even if no crewed starship launches within our lifetime, these advances reshape life here at home. But perhaps the greatest gift lies elsewhere. An impossible question asks what kind of civilization we hope to become. Once survival on a single planet becomes less uncertain, challenges worthy of an entire species become increasingly rare. Interstellar travel remains one of them. Perhaps that is why the question refuses to disappear, not because we expect an immediate answer, but because some questions are valuable precisely while they remain beyond our reach. Every ending eventually becomes another beginning. That perspective feels especially fitting here because our story does not close with an answer. It closes with a horizon that remains exactly where it has always been, waiting with complete indifference for whoever may one day cross it. The first crew to leave the solar system, if such a mission is ever launched, has almost certainly not been born. The propulsion system that carries them has not yet been invented. The civilization that assembles their vessel may differ greatly from the one we know today. Even the language spoken aboard that ship could sound unfamiliar to every person alive in our century. but the physical rules governing their voyage are already written into the fabric of the universe. The destination was confirmed in 2016. Researchers working today, across laboratories, universities, and space agencies on every populated continent, continue identifying the obstacles that stand between here and there. Those obstacles remain unchanged. The distance to Proxima Centauri is 4.25 light years, which is about 40 trillion kilometers, that is nearly 25 trillion miles. At the speed of Voyager 1, the journey would require roughly 75,000 years. None of those values bends to determination alone. The universe does not shorten the route because the destination matters deeply to us. Light does not travel faster because our questions are sincere. Nature offers consistency before comfort. But people can change. Across history, impossible frontiers gradually became understandable through patience carried across generations, knowledge accumulated, tools improved. Questions once dismissed as fantasies became engineering projects. Every advance depended upon individuals willing to begin work whose final outcome belonged to descendants they would never meet. Interstellar travel may demand that same kind of inheritance, measured not in years but in centuries. Seen from that perspective, the question we began with receives an honest answer. We still cannot know whether the first humans to leave our solar system will arrive. What we can know is the landscape between departure and arrival. Science has mapped the radiation, the isolation, the engineering, the biology, and the immense gulf separating neighboring stars. A map is neither a promise nor a warning, it is the beginning of navigation. Meanwhile, Voyager 1 continues its passage through interstellar space. Its instruments will eventually fall inactive, yet the spacecraft itself will keep moving among the stars. The golden record remains fastened to its side, carrying sounds, music, greetings, and fragments of one small world into distances beyond any human lifetime. It travels because people chose to send it. That decision revealed something enduring about our species, long before the spacecraft crossed the boundary itself. The nearest star remains 4.25 light years away. That has always been true. Only now do we finally understand what that distance means, and perhaps that understanding is the first real step of a journey whose destination still waits beyond the night.